if you add up all the forces acting on some chosen object, that's F net, and forces are vectors, so you have to express them in components and then add them. That's equal to the mass of that chosen object times the acceleration of that object's center of mass. I defined mass, and really up until now in this class, we've been mostly talking about what these accelerations mean. So we know how to calculate the acceleration of an object. We know what the mass means. Now we have to focus on what these forces are. Usually, we're not going to want to know something about the net force. You know, we won't want F net itself. We'll want to know something about the individual forces that make up F net. So in a case like that, you always need to draw a free body diagram. And I'm going to abbreviate free body diagram FBD. So we're going to basically use this anytime we use Newton's second law. The only exception is if it asks you specifically for F net, then there's no reason to do this because it's really only helpful if you're trying to break up into individual forces. But okay, let's talk about what are the requirements for a free body diagram. The free in free body diagram, or the free body, means the only thing you draw is the chosen body. Any other objects are only represented by the forces they apply to the chosen body. So any other objects show up only as the forces they apply to the chosen body. Okay, so here are the steps for drawing a free body diagram. So let's say, as an example, as I do this, I'm going to do a free body diagram of this car. There's a person standing on the car. The car is super cool looking. It's got some flames, some lightning bolts. There's an American flag because flags are rad. Okay, so let's say that we want the free body diagram of the car. So the first step is draw a closed outline of the chosen object. And this closed outline should not include any internal details or any outside objects. Okay, so in this example, that means that I'm going to draw an outline. It doesn't have to be very artistic, but okay, so there's an outline of the car. It doesn't have any, it doesn't show the lightning bolt or the windows or the hubcaps, and it doesn't show any external objects. Okay. So here are some examples of things that don't meet these requirements. Okay, that's not an outline because it doesn't say anything about whether we're including the top of this line in our chosen body, or the top of the hood or the trunk, and the wheels are closed on their own. The top is closed on its own. We want an outline that makes a very clear distinction between what's included and what's excluded. Okay. How many people here took physics before this? Any physics before? Not a ton of people, few. I think it's probably pretty likely that in your physics classes before, when you did free body diagrams, you did them as a point, and then you drew the forces going in the different directions. There's a reason that we're going to start doing it differently now. And that's that almost everybody in here is going into engineering. And drawing your free body as a point is useful for particle calculations, okay, where you assume everything is happening at a single location. But it's not useful if you're treating things as rigid bodies where you can make distinctions between different orientations of the body. Okay, because so if you're treating something as a particle, then there's a force acting on this wheel and a force acting on this wheel and a weight in the middle or whatever. But if it's a particle, you treat it like it's all acting on the same thing. So drawing this as a point and just different arrows in different directions is fine. But pretty soon, we're going to want more information than that. And like, for example, if you have a 5,000 Newton force on this wheel and 40,000 Newton force on this wheel, it adds up to a total force of 45,000 Newtons. But that's not the same as applying a 45,000 Newton force through the center of mass. One of those would keep it horizontal, and one of those would rotate it, And as a car owner, it's really important that you don't, you know what I mean? There's a big difference between your car being on its roof or not. Okay, so yes, so if you're used to drawing your free body diagrams as just a point with arrows coming out of it, you're going to have to change now, and you'll be happy you did when we get onto rigid bodies. Okay. So this won't work. this won't work. Where you're like, yeah, I did the outline of the car, but then I had to get that rad flag in there. That won't work because all we're trying to do is be perfectly clear about what's in the in crowd and what's out. You know what I mean? This that boundary is everything, and I'll explain why as we go. But the boundary between the in and the out is everything that we care about. Um, okay, so once you have that outline, the second step is uh, represent all forces acting on the chosen object. Um, by an arrow pointing in the direction of the force. And um, a value or variable that's going to represent the magnitude of the vector. Okay, so the magnitude of a vector, is that a number or a vector? The magnitude. It's just a number. So this is a scalar. You know, a scalar is says that that is just a numeric value or a single variable, not a vector value or a vector variable. Okay, so for the example that we're doing here, we haven't talked yet about how to know what directions these forces are applying, but I'm gonna put the directions here. But that's a lot of what we're going to talk about in the next day or two. So there's a weight force, and then each of these two wheels has an upward force applied to it by the ground. I'll call this N rear and N front. And then what else is going on? There's a guy standing on the hood. So there's a contact force of the feet of the person pushing down. I'll call that R. Okay. And now every object that's applying a force to this car is represented by a force vector. Well, this mg usually is known. We usually know the mass of the object, so forget about that one. But we have three of these things left over. And that means that if we go into Newton's second law right now, we would have three unknown values that we'd be trying to calculate. Okay. And if you're doing it, you know, since we're starting out with particles, we're starting out with particle kinetics. Two of those forces are applied to this object by a single thing, the ground. Okay. And so for now, breaking it up into the rear and the front, isn't really necessary. Um, so you can just do it as the weight force, a combined force from the ground, and then the force from the person. But like I said, when we start talking about rigid bodies, it's going to be important not to do that. But we have plenty of time for that. Okay, so this is a complete free body diagram. Now, before we go into talking about the directions of individual forces, I think one thing that's always going to be important to keep in mind is how do you know once you've represented all the forces? So how do you know if you've represented all the forces? Yep.
If you know the object isn't moving, all the forces should add to 0.
That's true. That's not what I was getting at right now. But that is going to be a useful thing. So, like, look at this complicated, you know, sort of a complicated picture. There's just a lot of stuff going on. There could be a million people milling around or whatever. How do you look at a picture like that and know whether you've represented all the forces? Well, there are only two types of forces. And if you've dealt with all of those types of forces, you know you're good. So the two types of forces are first, what I'm going to call field forces. And by far the most important of those for us is gravity. But that could also involve magnetic fields, electric fields. There's probably other ones. So basically, we're only going to deal with gravity. And that's a downward force with a magnitude of mg, where m is the mass of the chosen object, and g is the acceleration of gravity in free fall, 9.81 meters per second squared. Okay. If you have an electric field or a magnetic field or whatever, things can get a lot more complicated, but we're not going to really have to deal with that. So for us, you just have to make sure that you draw that weight force in there. And then after you've dealt with the weight and any other field forces that are happening, there's only one other type of force that you have to deal with, and that's contact forces. And that's forces that are applied to the chosen object by the surroundings. At the boundary. And that's why we want to be so careful about defining what is the boundary between what's in and what's out. So let's look at this object again. In order to make sure that you represent all the forces that are applied to this object, we first show the weight force, this downward force of mg. And now the only thing we have left to do is mentally go around the boundary and think about, at that point on the boundary, is there any contact between the surroundings and the body? Okay. Once we've dealt with all of those places where there's contact, we're done with the free body diagram, and we know that we have every force represented. Okay, so there's a weight force, and now I'll just start arbitrarily at the front wheel. There's contact at the front wheel, so you got to put something there. Keep going around, nothing, nothing, nothing. Up here, there's the guy standing on the hood, so we have to put some kind of force there. Nothing until you get to the back wheel. There's contact between the surroundings and the boundary there, so you need a force there. Go around, and then you're done. Okay? So no matter how complicated the thing is, your free body diagram, to do your free body diagram, you're going to represent the weight force, and then you're just going to go around the boundary looking for contact. And once you're done with all the contacts at the boundary, you're done with the free body diagram. Okay? Okay, so for the gravitational force, I said the direction that it acts, it's always down. And by the way, notice that this doesn't say anything about what the object's doing, whether the object's flying through the air or sitting on a table or whatever, the gravitational force is always the same, okay? So if you're ever asking yourself, like, wait, is there gravity here, or does this change it or whatever, in a way, you're already thinking about it too hard, you know? The answer is gravity always applies a force magnitude mg down, you know? And like, oh, but what if I'm floating in a tub of goo or whatever? Well, gravity still applies that weight force down, magnitude mg. It's just the goo also applies a force upward that keeps you from sinking. Okay. I just wanted to say tub of goo. All right, so we know the direction of the weight force. Now we have to think about the directions of various types of contact forces. And there are going to be 4 of these types. The first one is a pushing contact. And a pushing contact is one where, so if this pushing contact force didn't happen, the 2 objects would blend into each other. Okay, so it resists like merging. The second type is a pulling contact. And an object is pulling on another object if that force is preventing the 2 from separating. So this resists separating. The third one is a friction force. And the fourth one is a spring force, a force applied by a spring. The first three seem it's pretty intuitive that those come up often enough that we'd want to deal with those. I think probably to a lot of people, that fourth one seems pretty random, like your parents' house has a junk drawer in it that has like springs in it, but it also has like a broken pair of sunglasses and like some glue or whatever. Like, why aren't we doing sunglass forces? You know what I mean? The answer for that is that actually the kind of forces that springs apply are called elastic forces. So really, that's the start of talking about elasticity. And elasticity is a really useful idea in engineering. When you when a machine applies a compressive force to a piece of steel or whatever, that compressive force makes the steel shorten a little bit and bulge out on the sides a little bit. It's very little because steel is really stiff. But that process is elasticity. It says that you apply a force, you get a change, you get a deformation of the material. When you remove the force, the thing goes back to its original shape. And a lot of important engineering stuff depends on that idea. So really, don't think of this as us doing calculations involving springs like that you get at the hardware store. Think of it more as like an introduction to this idea of elasticity that's going to be important.